Okay, let's go ahead and get started. My name is William Moyes. I'm an architect at AMD, and I am the editor for the SNIA SDXI specification. And this is Shyam Iyer. He is the chairperson for the SNIA SDXI technical work group. And today we'll be talking about SDXI, obviously. So we'll start off with a brief introduction to SDXI, just out of a show of hands. How many folks here are aware of SDXI, have looked at it, et cetera? Just a few. Good. Well, I don't know if that's good or bad, but it's a thing. And I'll spend a few minutes describing more about what SDXI is and what it's about. Then we'll get into what we've changed, what's new to SDXI 1.1. And then we'll start going through those new features. And we'll spend a few minutes at the end talking about what you heard this morning about storage.ai and how storage AI and SDXI will work together. So to start off with, let's cover the basics. What is SDXI? Honestly, I think about it, the easiest way to explain what SDXI is to compare it to other industry specifications. Think about what NVMe does. NVMe defines a hardware to software interface for solid state disks. And it defines that interface, and therefore you can build your software stacks, your OS drivers, et cetera, all against that generic vendor-neutral specification, and can work with a whole host of different hardware by different providers. SDXI is doing something similar, but for data mover accelerators, DMA engines, providing that layer of abstraction and that standardization. SDXI itself is a modern design that supports shared virtual memory, virtualization, and user mode accelerator use. As part of this being standardized, just recently, earlier this month actually, a SDXI driver was submitted to the Linux kernel mailing list for review and comment. And so you can again see how that benefits the community. When it comes to the features such as shared virtual memory, this is really about simplifying the programming model. As a user application with shared virtual memory, it means that your application can use its native virtual memory addresses when interacting with the hardware. So you look at what's happening in the industry, this transition towards user mode applications, where you have user mode drivers directly interfacing with the hardware. This makes a standardized interface like SDXI all the more important, and it also allows, with the shared virtual memory, allows the applications to use those native virtual memory pointers. So an application you can request from the operating system its ring buffer for submitting commands to the hardware, and then it can submit those commands using regular unpinned virtual memory. So if you wanted to, and not that I recommend this for a bunch of reasons, but in theory, you could take a variable on your local stack and pass that directly to the SDXI hardware and have it manipulated. Again, don't recommend it, but it's theoretically possible. The page faults, et cetera, will be handled by the hardware and the hardware's direct interaction with the operating system. And user mode applications wouldn't need to be concerned with it. SDXI also is address space aware. What I mean by that is, because it's working with shared virtual memory, it has an understanding of the different virtual address spaces that may exist inside of a system. And what this allows is app-to-app data motion without the need to perform a context switch to the operating system. In fact, you can do application-to-application communication even if they're running inside different virtual machines on the same system. So with this, imagine what you might be able to do with a software-defined storage type application, where you can have an application communicate with the other layer, and there isn't the need to go through the local operating system transition, going to the hypervisor, back down to the remote operating system, and then back down to the other application. So it can cut out all those context switches that would otherwise be necessary. SDXI, it was also architected to allow for extensibility and to allow for additional offloads to be added. And we're going to spend more time today during this presentation talking specifically about that feature and specifically what that brings to bear. So kind of the big question is, what do we do? What do we change? What's brand new to SDXI 1.1? Honestly, this is a rather lengthy list, and I don't want to bore you guys to death. So I'll just hit a few highlights as we go through this. If you have questions, feel free to ask after the presentation is completed. We are kind of pushed for time here, being a 25-minute presentation, so please come up to us at the end. Or when, if you don't have time during this session, please catch us during the remainder of the conference. to ask any questions you might have. So as far as the features go, we've made some improvements and additions for memory synchronization purposes. We've added a new read barrier capability to handle, to better allow software to handle a read after write type hazard. Before this, there was a need to do a full execution fence, which is rather costly. This has been addressed with 1.1 with this new read barrier capability. There were also enhancements to the write immediate command, a command that can go out and write to a particular selected memory address a value. By adding these atomicity guarantees, it makes it easier to use this operation to do things such as chaining between different hardware devices, be able to have the SDXI function go trigger another device's doorbell register, for example. It also helps with lockless data structures, where again you have those atomicity guarantees we can fall back on. There are a number of extensibility and flexibility improvements. Some of these improvements actually involved making certain required features in 1.0 optional in 1.1. So for example, the need to support peer-to-peer operation has actually been relaxed, where hardware can opt into saying, actually, no, I'm DRAM only type of an approach. Likewise, support for some of the mailbox schemes is no longer mandatory. There have been important improvements to the text, for example, surrounding confidential memory use cases, and also there were some notable changes relating to error handling, and ensuring security around error handling have gone into the text. And of course, we've had a number of new operations that have been added. And I'll spend the next few minutes talking about those new operations that are brought into the spec itself. So here's a list of the SDXI 1.0 and 1.1 operations. These are the actual commands that an SDXI implementation can execute. Many of these are actually optional. There's a discovery mechanism, which we'll talk about here in a moment. And as you can see here, SDXI 1.1, there's a lot of features that are there for signaling purposes, communication. With SDXI, it is a lot of traditional schemes. You would submit work, and you would say, give me you have an interrupt when that work is completed. With SDXI, it's more of a software-defined scheme. You can choose to use atomic updates to semaphores, or you can choose to use an interrupt delivery. And you basically have the opportunity to roll your own signaling and response mechanisms with the way SDXI was architected. But when you look at SDXI 1.1, the primary workhorse is that memory copy operation. Take something from source, copy it over to destination. Getting into SDXI 1.1, a number of additional operations have been added that you can see here on the list, and I'll go through those in a bit more detail as far as the capabilities, such as the CRC capability, the compare operations, and the protection information capability. But one other important thing I want to highlight here is, if you notice, starting with the new commands for SDXI 1.1, you can see on the far left you have the type. That's the opcode type, and the opcode type is actually split into a type and subtype, and then the subtype column. But then for the 1.1 commands, you'll see their function assigned. The function assigned concept is a new capability we've added to SDXI 1.1 to allow it to be much, much more extensible than SDXI 1.0 was. So let me give you a little background about how SDXI opcodes work. Like I showed earlier, the different opcodes are broken into the type and subtype fields. And we've organized the operations into what we call operation groups. An operation group is a set of related commands that share the same opcode type field. They are discovered as a group, so the whole group's present, the whole group's not present. Also, when it comes to access control, when the hypervisor or operating system selects what a particular process is allowed to use, the opcode, the op group is used to select and say, yes, you're allowed access, or you're not allowed access. With SDXI 1.0, the 1.0 spec was provisioned to allow an SDXI function and implementation to support up to 32 opcode groups. Beyond that, there wasn't full provisioning, even though the actual opcode space was 2048 in size. And of those 32 opcodes, 4 were reserved for vendor usage, leaving 28 available for SNIA definition. And taking a step back and looking at that, that's kind of constraining. As we're adding new opcodes, we exhaust that space fairly quickly. And then when it came to the vendor-defined capability, the option for the vendors and researchers to innovate, that was very limiting. There was also a restriction that There wasn't a good scheme for doing detection for a vendor capability. There wasn't a good solution for handling namespace collisions. And so as it was in 1.0, it was really of limited usefulness. So we took a step back, rethought how we were going to approach the problem, and created a backwards compatible solution with SDXI 1.1. What we've done is we've added a new scheme that there is an administrative command that can be executed that will provide back to software a list of all the supported operations. These operations come back and are identified by a machine-readable 128-bit globally unique ID, or GUID. So basically, software goes to the SDXI device, which it can identify in the case of a PCIe device by its class code, and it will ask the device, what can you do? The device comes back with a list. I can do all these things, and by the way, here's the opcode numbers you use to access these feature sets. And then software can then say, oh, I know what this one is, and I can take advantage of that, and it can grab it, and it can use it. It may see someone there it doesn't recognize, it may see someone there it doesn't want to use, but it can see the entire list. And this way we have the flexibility and the extensibility for SNIA's use, and also for everyone else's use too. Basically what this means is that not only can SNIA introduce new opcodes by defining a new GUID and publishing it in the official specifications, research labs, individuals can come in, implementers can come in and say, I want to create something. They can create it, develop it, and still leverage a large part of the software ecosystem. And only when you get to the application level do you really start having to worry about some of those details, providing you're given access to your resource. It's very, very powerful. And not only that, with this scheme, if there is a capability that is developed, it is possible to donate that IP, that vendor extension, if you will, back to SNIA. And SNIA can then adopt it with this scheme, meaning that it could then become part of the official standard, and it won't disturb the software ecosystem. Because software that did exist can still see it, can still use it. The hardware that exists will continue to work. So as new software gets developed, it'll continue to work with the old hardware, and likewise, the existing hardware will continue to work with the software moving forward. It's quite a clever scheme. Okay, moving on. Let me spend a few minutes talking about the actual commands. Again, the bread and butter of SDXI was that memory copy operation. That's been augmented by a memory set. SDXI 1.0 did have a rep copy to take a 4K block and make many duplicate copies of it. But now there's a regular mem set, more like the kind of the C-style mem set, if you will. There's a memory compare, again, similar to what's available in the C and other programming languages, where you can go in and do compare two buffers and get a greater than, equal to, or less than type response. And it will also identify where inside the buffer the delta occurred. There's also a compare immediate operation, so again, comparing two buffers, but the buffer is actually just an immediate value repeated. This is useful if you want to know, is this buffer all zeros, or what's the first non-zero value in the buffer? Again, it's a capability that's been added in. There's now a double copy operation, a single source dual target. We had a fair bunch of discussion back and forth about do we want to do a 1-to-2 copy, a 1-to-n copy, ins and outs. After all is said and done, basically this feature can improve efficiency when trying to create multiple replicas of data. And it strikes that balance between simplicity of implementation and definition versus what's available, performance-wise. Also, 2 replicas is a fairly common case. So next up, we have the CRC offload command. The CRC command, honestly, is kind of your multi-tool for CRCs. This particular command does several things. Let me take a moment explaining what it's able to handle. First, it's able to handle 16 and 32-bit and 64-bit CRCs. It handles many of the common polynomials. For example, the polynomial used by pkzip, zlib, etc., that's covered. It covers the ones used by iSCSI. It supports the NVMe 16, 32, and 64-bit guard tag CRC calculations. All of those polynomials, bzip, again, these are all covered by this feature. The feature is able to go in and take a buffer of data in memory and run the CRC over it for 1 to 4 gigabytes of data. It is possible to take a CRC calculation that's completed and use that as the input to a subsequent CRC calculation, to continue the calculation. So if you need to go across multiple buffers, or you had something very, very large you wanted to calculate, again, fully able to do that. It's able to do a copy while doing the CRC. So that's an option. You can take a data buffer, and as you're copying it, you can calculate the CRC over the data while it's being copied. And there's also a block mode. So instead of looking at one giant contiguous buffer, you can say, here's a buffer of data consisting of many 512 byte or 4K blocks sectors. And it can perform the calculation on each one of those sectors individually and give you the list output of the results. And last but not least, is this doing all this, if you are doing a block operation also involving copy, this feature will let you go in and optionally insert gaps to insert metadata. So if you have a data format where you have block of data followed by some metadata, say for example for guard tags and the like, it can insert those or remove those as it's copying the data and performing the CRC and doing the bulk data copy. And so it's quite a flexible tool to handle a lot of different applications that come up. Okay.
All right, so it's all about building on operations, right? So we had 1.0 base copy, and then we had a few set of offloads that we could offer. 1.1 brings in a whole bunch of new other operations. And then as we were talking about CRC, CRC is also the base for doing more interesting things like diff-dix operations, like what Protection Information Group is trying to do, which is basically, can you also do diff checks or diff inserts or diff strips or diff updates and diff compares? So it's solving the use cases for when data, loss of data can be very catastrophic. And so if you're already building CRC-enabled hardware or for offload capabilities, you can also add all of these operations as part of the whole data protection stack, right? And so we have made sure that the opcodes are sort of compatible with the CRC data structures. So from that base CRC implementation, you could also offer potentially some of these PI operations. And that's one of the reasons that SDXI kind of builds on a framework. So you have software stacks that are compatible, but also from a hardware point of view, you can build over as layers. So now I want to talk about a little bit around SDXI and storage AI. And I think some of you have heard the conversations today morning around storage.ai, and then SDXI was mentioned at least 1 or 2 times. And I just wanted to kind of talk a little bit about how this fits in. I think Jay mentioned that it was designed with virtualization in mind. I think I'll flip that a little bit. In an architected system, no one talks about, is a BMC a component that is used only for virtualization or systems management? A BMC is an architected device. I think when we consider SDXI, it's an architected data mover, part of the platform. It can be used for any kind of use cases. I have a big hammer and I see everywhere a nail. So it is certainly a very powerful tool in the sense that memory data movement is integral to a lot of operations, which includes virtualized environments, which includes bare metal accelerated environments, and also includes AI. So when we say we can envision an SDXI use case in an AI workload, it's about where's the memory data movement happening? Is it happening between CPUs memories, between CPU and NPU memory and NPU, GPU memories or DPU memories? Wherever you have memory data movement happening, SDXI is part of your topology. The fact that SDXI can access multiple address spaces and is built up grounds up to specify here's a CPU memory address space, or maybe this is another CPU memory address space, and by extension, some other device's memory address space, means that you can inherently take advantage of the standard to target different memory address spaces. We also talked about virtualization. The fact that Accelerator interface is virtualization ready means that you can have workloads running in guest virtual machines, even for AI, that are based on the guest virtual address space and still directly target the Accelerator interface. The new opcode feature that William talked about is critical in the sense the way we can unlock innovation is by allowing accelerator vendors to come up with their own kind of operations, whether it's a new matrix multiply, whether it's some kind of a data transform that is specific to prepping your data before it gets fed to other accelerators, let's say GPUs, or if you're doing post-processing, there's fair amount of data prepping and data conversion involved everywhere. And so these type of new opcodes are going to be essential in offloading some of these operations. And SDXI provides you the framework where you can now rest on a software architecture that depends on a stable framework. To me, the analogy is really like ISA extensions. So we're building an ISA extensions for accelerator offloads, and that's how you can get the most out of your TCO value. So one of the good things about having a standard is having more people talk about it. William is a classic example of, he joined the work group right around the time we were releasing 1.0, and he's now the editor of 1.1 and specifying a whole bunch of new operations and workflow here. And I think that's kind of what we want out of the community. We have a really interesting bunch of people working on this. So please come join the work group and help. If you don't see an offload operation that you love and you prefer to have it in the standard, then you are the right candidate to come talk to us. With that, I guess we are almost there, and we have time for Q&A.
Go ahead in the back.
One question is from a confidentiality point of view, or at least the keys effort is
Yep.
more or less well-defined in PCIe. And if it is memory movement between virtual machines or portions of virtual machines or portions of memory that are mapped between virtual machines, what kind of access control or what kind of mapping you have for these?
Yeah, that's a great question. So when it comes to what's that? So the question was, how does confidential compute work with the? Is that not working? Okay. So the question was, how does confidential compute work with technologies such as TDISP, et cetera, and SDXI's ability to move data from VM to VM? That's actually a really good question. So first, let me answer this part. SDXI already has inbuilt capabilities to be very selective about who is allowed to do what, crossing VM boundaries. There are access controls, R key, A key. You can read about those inside the specification. So given that, it is, I am quite confident right now that if you had a particular VM and the VM wanted to use the SDXI capability offload for its own internal use, you're good, right? The capability to support what's needed is there. When it comes,
Which includes different address spaces within the same.
yeah, different address spaces within the same VM. That's fine. When it comes to doing the cross VM, you can restrict it. That's fine. When it comes to a particular VM going cross VM, there's a little bit of a gotcha that we're working on ironing out. So we do recognize that, and if you want, we can talk later about that in more detail.
And just to add, right, I mean, in terms of this, the current TCB we're considering is the VM and that function. So that TCB envelope is right now that VM and the function that is associated with it.
William, I had a question about the atomic support that you have in 1.1. I'm assuming that's PCI?
It's actually goes, so the question was about the atomics. It's actually, there's two layers of atomic support. One layer is PCIe atomics, so a SDXI implementation running against pure PCIe would be limited to that. What's available in 1.0 and 1.1 is actually an extended set of atomics that go up and beyond what is supported in PCIe. So if you had a device connected to something a little beyond PCIe, you could then utilize the full atomic support. Oh, as far as the lengths go, so the question was about the atomics size. The difference is the extended atomics group is really supporting, or the full atomics group is supporting a wider variety of operations than PCIe supports. But as far as the actual width of each atomic target, you're limited to either 32-bit or 64-bit. No 128 or 256 at this time. Good question. Other questions?
But I think if someone wanted to implement that, the standard is extensible, and you could keep increasing the width. Yeah. Yeah. Time's up. So that's time. Thank you so much. And we have another SDXI topic after this, so stick around.